Okay, we're going to start with our second part of the exam review for exam 3, chapter 7 and 8. The bulk of the questions from this part of the review will be for chapter 8, with a few more from chapter 7 towards the end of the review sheet. First question, so these will be our first 3 that we'll look at, so you can refer back to this for the questions if you don't have your review sheet handy. First question says, according to the kinetic molecular theory, if you decrease the volume of a gas at constant temperature, the pressure will decrease because, um, remember what, uh, like what causes pressure? Okay, remember what we talked about when we were talking about the big thing that causes pressure is the number of collisions that gas particles have with the walls of their container. Anything that you do that increases the number of collisions is going to increase the pressure. Anything that you do to decrease the number of collisions is going to decrease the pressure. So if you decrease the volume of a gas and you kind of keep everything else the same, then the gas is going to have a smaller space to exist in. And so as those particles are moving around, those particles are going to find the walls of the container more times, right? And so the more times that they find the walls of the container, the more times they're going to impact the walls of the container. And every time that they impact the walls of the container, they're going to create pressure. So choice A describes the reason why there's going to be a pressure increase because the gas molecules are going to strike the container walls more often. And this is going to cause an increase in that pressure value. Okay. All right, our next 2 questions are conversion questions. Number 32, we're going to be converting from the torr unit into millimeters of mercury in atmospheres, and we'll see which value matches with our answer choices here. And then for the second one, we'll be going from atmospheres into millimeters of mercury. For a question like this one, like number 32, um, when you're looking at this question, like sometimes it can be confusing, like what they want you to do. Here, they give you your initial value of 648 torr. And so the easiest thing to do is to convert torr into millimeters of mercury and then convert torr into atmosphere. And then only one of these answer choices is going to match the number as well as the unit. But you have to make sure that both of those things match. Okay. All right. So let's try that one out. We'll write down the answer choices as well. So we're starting out, question number 32. We're starting out with 648 torr. And our answer choices are 0.852 millimeters of mercury, 760 ATM, 1.17 millimeters of mercury, 0.853 ATM. Okay, and we're going to remember that our conversion for torr and millimeters of mercury, every 1 torr equals 1 millimeter of mercury. So if we have 648 torr, that's going to be 648 millimeters of mercury because they're the same unit, they just have a different name. What that means for us when we're looking at these answer choices is that we can immediately get rid of both of those answer choices because we know that if it's 648 torr, then it's going to be 648 millimeters of mercury as well. So one of these choices has to be correct. Okay. What we also know is that every 1 atmosphere is going to equal 760 torr. And we're going to know this because of our list of pressure unit equalities that we want to be familiar with. So this is our equality that relates the atmosphere unit and the pressure unit. And so if we start out with 0 Wrong one, wrong number. We're going to start out with the number that they gave us here, 648 torr. And then we're going to say every 760 torr, right? If torr is on the top, then torr is going to be on the bottom so that the units cancel. Every 760 torr is 1 atmosphere. And this is where we get our 0.853 ATM. And that's how we know that answer choice D is the correct answer for that question. All right, for question number 33, they're having us convert from atmosphere into millimeters of mercury. And again, we can write down our quality for this that we know from our list of conversions. Every 1 atmosphere is 760 millimeters of mercury. So if they're going to give us 1.25 atmosphere to start with, we know that every 1 ATM is 760 millimeters of mercury. We see that our atmosphere units are going to cancel out. That's how we know that we have positioned everything the correct way. And we end up with 950 millimeters of mercury as our final pressure value in that case. That's answer choice D. All right. Let's look at the next set of questions. We'll put up the next 3 to look at. And what's going to be important in these next set of questions is paying attention to the properties of the gases that are mentioned here. Because remember, we have quite a few of those simple gas laws that we looked at before the ideal gas law. We have Boyle's law, we have Charles' law, we have Gay-Lussac's law, we have Avogadro's law, and the combined gas law. And all of those focus in on specific properties. And if you can relate the specific properties that are mentioned in the question with the law that applies to those properties, then you're going to know how to answer the question. It's not going to be a problem at that point. For example, in the first question, they're telling us that we have a 5-liter sample that has a pressure of 5 atmosphere. So this is volume, this is pressure. Then they're saying that the volume of the anesthetic that's given to a patient at a pressure of 1 atmosphere, so that's another pressure, is what? So in this case, we have a pressure and a volume. We have a second pressure and we're missing a volume. Okay. So understanding that pressure and volume are the 2 things that we're focused on here. I know I'm writing this out in my mouse handwriting. But this is going to be Boyle's law. Okay. Anytime that you're relating pressure and volume, that's going to be Boyle's law. So if we look at the next question, number 35, similar situation here. If a gas occupies 2 liters at 3 atmospheres, how many liters will it occupy at 6 atmosphere if the temperature isn't changed? So again, we have pressure and volume as the only units that are being mentioned here. So this is going to be another example of Boyle's law. So let's tackle those 2 questions. And then we'll see that in question number 36, we're moving on to volume and temperature. So that will be a different one of our gas laws. But for question number 34, they're telling us that we have an initial volume of 5 liters with an initial pressure of 5 atmosphere. And we want to know what volume of anesthetic is given to a patient if the pressure is 1 atmosphere. Okay. So when we have volume and pressure, the equation that we're going to use for that is P1 times V1 equals P2 times V2. Okay. And so we're going to plug in our values that we have. 5 atmosphere times 5 liters equals 1 atmosphere times V2. And our atmosphere units will cancel out. So the patient ends up getting 25 liters of gas. Okay. For question 35, our setup is going to look really similar because we're still using the same simple gas law. We're still using Boyle's law here. In this case, they're telling us that our gas is occupying an initial volume of 2 liters at an initial pressure of 3 atmosphere. And our pressure is going to change to 6 atmosphere. And we want to know what our new volume is going to be. Okay. So we still have P1 times V1 equals P2 times V2. So we'll plug in our 3 atmosphere for P1, our 2 liters for V1, our 6 atmosphere for P2, and then we'll solve for V2. Okay, and we can cross out our atmosphere unit, and we're going to be left with our unit in liters. So this is going to leave us with just 1 liter as our volume. All right. Now for our next 2 questions, we're looking at, maybe our next 3 questions, we're going to be looking at Charles' law. So remember that this law with pressure and volume, this is Boyle's law. Everyone's aware at this point that your exams are not just math tests. So you have to, there's conceptual questions on there too that you have to be comfortable with. Some of those concepts that you have to know, that you have to remember, are which of these laws relates to which properties. So you have to know that Boyle's law is the law that relates pressure and volume of a gas to each other and shows the inverse relationship between them. Okay. And then the next law that we'll look at will be Charles' law. And remember that Charles' law is going to have the formula V1 over T1 equals V2 over T2. And we'll put a little asterisk here so we can remember that our temperatures are always going to be in Kelvin. Okay. So question number 36. Tells us that we have a 2-liter bottle that is sealed at room temperature of 23 degrees Celsius. And it asks, what is the volume if at 0 degrees Celsius, if the pressure remains constant? So our T2 is going to be 0 degrees Celsius. Okay. So for any question with Charles' law, if they give you these temperatures in Celsius, the first thing that we have to do is add 273 and turn these temperatures into Kelvin. 6, 9, 296 Kelvin and 273 Kelvin. Okay. And then we can plug in and figure out our problem here. So we have our V1 is going to be 2 liters. Our T1 is going to be 296 Kelvin. Our V2 is going to be our question mark, and our T2 is going to be 273 Kelvin. So we're going to multiply both sides by 273 Kelvin. You see how our Kelvin unit cancels out there. And we're going to end up with 73 times 2 divided by 296, 1.84. As our V2. 1.8, I think is what it says on the answer key. Which makes sense because if we know that Charles' law shows a direct relationship between temperature and volume, which means if one goes up, then the other one has to go up as well. So if we have a bottle that's 2 liters at 23 degrees Celsius, if our temperature decreases, our volume has to decrease as well. Okay. So you can also like use your knowledge of the simple gas laws to help you eliminate some of the answer choices, right? So if you look, even for this question, if we can look at the answer choices that were available to us, we had 2.2 liters, 1.8 liters, 2.0 liters, 0.22 liters, 17.5 liters. Okay, those were the answer choices that we were provided with. We know that the temperature is decreasing. And because the temperature is decreasing, the volume has to decrease as well because our pressure is constant. So if our original volume is 2 liters, then when we look at these answer choices, any answer choice that is bigger than 2 liters is all automatically, we get rid of it. Any answer choices that's the same as what we started with, we have to get rid of as well because our volume has to get lower. So these would be the only answer choices that we could even pick in this scenario. And our work is to prove which of these are going to be the correct answer. Okay. So if we can use some of what we talk about, like I said, with the concepts, that can sometimes help you in like your multiple choice test because you can reason out which of those answer choices don't make sense even before you start. Okay. All right, let's look at question number 37 next. Let me just show the questions again in case anyone doesn't have the sheet, just so you could see the questions and the choices. Okay, so this one says if a gas occupies 5 liters at 298 Kelvin, what temperature is needed to reduce the volume to 2 liters if the pressure doesn't change? In number 38, which we'll do right after number 37, without coming back to the shared document. It says an automobile tire is initially at 32 psi at a temperature of 25 degrees Celsius. What is the pressure after 100 miles of driving if the tire's temperature is now 50 degrees Celsius and the tire's volume remains constant? That's a different kind of question. So actually, that's not Charles' law. That's the combined gas law. So we'll look at that. We'll talk more about that when we get to it. But number 37 is still just Charles' law. Okay. Oh, I mean, number 38 is a Gay-Lussac's law, rather. All right, so for this one, again, we're looking at, we'll set up our variables first. I think that that's the easiest way to start. We have V1 is going to be 5 liters, and T1 in this case is 298 Kelvin. Very helpfully already gave us a temperature in Kelvin. And they're telling us that V2 is going to be 2 liters. Okay. The answer choices that were given here: 10 Kelvin, 63 Kelvin, 119 Kelvin, 305 Kelvin, 745 Kelvin. What we see here is that our volume is decreasing. Write that over here. They're telling us our pressure does not change and our volume is decreasing. If our volume is decreasing, then our temperature has to decrease along with it. Okay. If our original temperature is 298, that means that any temperature that's bigger than that can't be the right answer. Okay, so we've already eliminated 2 possible answer choices. Now we're going to figure out what the right answer is going to be. Okay, now remember that when we're solving for a variable that's on the bottom, it's going to be easier for us to solve for that variable before we plug in our numbers, because solving for that bottom variable is a little more annoying than solving for something that's in the numerator spot. So when we start out, we'll write out our equation. And remember that the first thing that we're going to do is we're going to take that second temperature and we're going to move it up into the numerator spot by multiplying both sides by T2. So we're going to cross it out from the right side, and now it's going to be over on the left side. Okay. So we have T2 times V1 over T1 equals V2. All right. And now we want to get T2 by itself. So we're going to multiply both sides by the reciprocal of these numbers. Okay, so we're going to take, basically we're moving the reciprocal of this to the other side. But we can show that mathematically by saying that we'll multiply this side by T1 over V1 so that it crosses out. And we multiply this side by T1 over V1. And now what we're left with is that T2 equals V2 times T1 divided by V1. So from our original equation, we move T2 to the top of the other side, and we move the reciprocal of what was on the left side over to the right side. And now that we have this version of our formula, now we can plug in the numbers that we have. So we're going to plug in 2 liters for our V2, 5 liters for our, 298 Kelvin for our T1, and then 5 liters for our V1. Our liters unit will cancel out there, and we'll be left with our Kelvin unit. And we end up with 119 Kelvin, which is one of the answer choices that we narrowed it down to. Okay. All right. So the next question, um, which I'd originally, when I did a quick read of it, I thought it was another Charles law question, but that one's actually asking about pressure and temperature. And pressure and temperature is Gay-Lussac's law. Which looks a lot like Charles' law in its setup. It's going to be P1 over T1 equals P2 over T2. And again, your temperatures have to be in Kelvin. Okay. So question number 38 tells us an automobile tire is initially at 32 psi. PSI is the pressure unit, pounds per square inch. And a temperature of 25 degrees Celsius. What is the pressure after 100 miles of driving? So our unknown is going to be this new pressure. If the tire's temperature is now 50 degrees Celsius and the volume remains constant. Okay. Um, so the only thing that we have to change before we get started is we have to turn these Celsius temperatures into Kelvin. Okay. So our P1 is going to be our 32 psi. The units for your pressure don't matter in your simple gas laws, like in Gay-Lussac's law or in Boyle's law. The only thing that matters in terms of the pressure unit that you use for these calculations, they have to match each other. So if you use PSI here, we're going to be solving with a PSI unit for pressure too. Or you can convert them both into atmosphere if you'd like. You're going to notice that, again, this is another question where the answer choices, they're being a little bit tricky with them because they have answer choices with a mix of different units. And so when we calculate this final answer, we have to verify that our number and our unit both match the answer choice that we pick. Okay, so we'll leave those here for us to look at shortly. So our pressure one is 32 psi. Our temperature one is 298 Kelvin. Then we have P2 over 323 Kelvin. So we're going to multiply both sides by 323 Kelvin. See that our Kelvin unit cancels out. Okay, excuse me. And so actually that there's no super trick here because we see 34.7 psi, 34.7 psi. So that's our good answer there. It would have been trickier if this wasn't an answer choice and if they actually put like um the answer in terms of like atmosphere as an answer choice. Like this is the answer that we got. We know that from our conversion, our equalities for our pressure units that there's 14.7 psi in every 1 atmosphere. So this pressure is also equal to 2.36 atm. If this was an answer choice instead of this, then you could have picked this answer choice and it would still be correct. So that's just the kind of thing that you want to be on the lookout for. That's why you always want to match your number and your unit. Okay. All right. So let's take a closer look at number 39. Well, we'll look at the next three. The next three up to look at. They're giving us a sample of gases, a volume of 6.50 liters at 845 millimeters mercury and a temperature of 25 degrees Celsius. They're asking us for the pressure of the gas in atmosphere when the volume of the gas is 12.8 liters and the temperature is 47 degrees Celsius. So they're changing the volume, they're changing the temperature, and they're asking us to find the new pressure. When you're working with three variables instead of two, that's when we're working with our combined gas law. Okay. And the combined gas laws is like its name. It looks like a combination of those other gas laws that we looked at. Okay. And in question number 40, it says a sample of methane gas has a volume of 10 liters at a pressure of 1.5 atm and a temperature of 20 degrees Celsius. What volume does the gas occupy if the pressure is lowered to 0.9 atm at a temperature of 40 degrees Celsius? So this is another example of the combined gas law when they're giving us three properties to work with. In this case, they're changing the pressure and the temperature, and they're asking us to find the new volume. Okay. So let's take a look at both of those. So yes, first, actually, let's write out a reminder of what the combined gas law looks like. So it looks like a combination of Boyle's law and then Charles/Gay-Lussac's law. So pressure and volume on the top, temperature on the bottom, then pressure and volume on the top on the other side, temperature on the bottom. So for question number 39, they tell us that we're starting with a volume of 6.50 liters at a pressure of 845 millimeters of mercury and a temperature of 25 degrees Celsius. And we're going to be changing it to a new volume of 12.8 liters, a new temperature of 47 degrees Celsius. And they want us to find that missing pressure. They also explicitly want us to find that missing pressure in terms of atmosphere. Okay. And that unit change is going to probably impact the way that we plug values into our equation, because it'll be easier to change this value into atmosphere before we plug it in, to make sure that the number that we get back out in our calculators is already in the unit that we are looking for. Okay. So let's take our 845 millimeters of mercury and switch it into atmosphere. So we'll put our 760 millimeters of mercury on the bottom, 1 atmosphere top. $45. And for our temperatures, we'll add our 273. Okay, and now we can plug in and solve for our missing variable. And in this case, our missing variable is going to be P2. So we'll have P1, which is the pressure that we switched into atmosphere already. And we're doing this because the answer choices, if you look at them, they're all in atmosphere. And so what we don't want to happen is for us to plug in 845 millimeters of mercury, solve our whole problem out using the 845 millimeters of mercury, and then end up with an answer in our calculator that matches a number here, but the unit doesn't match. It's really easy to do that. And that's always a bummer when you've done the steps correctly, but you miss that last step of converting it into the correct unit. So because all of these units are in atmosphere, that's why we switch this from millimeters of mercury into atmosphere. Okay. So that's our P1. Our V1 is 6.50 liters. Our T1 is 298 Kelvin. Our P2 is our question mark. Our V2 is 12.8 liters. And our T2 is 320 Kelvin. And now we'll multiply both sides by the reciprocal of what's on the right side. Right, so these will cancel out. And we'll multiply the other side by the reciprocal as well. Our Kelvin unit cancels out, our liters unit cancels out, and we're going to be left with a unit of atmosphere. Okay. So we get our P2 value. All right, for question, that was question number 39. Oh yeah, right over there. So let's do question 40. Still a combined gas law question. So here they tell us that we have a sample of methane gas that has a volume of 10 liters at a pressure of 1.5 atm and a temperature of 20 degrees Celsius. And then it asks, what volume does the gas occupy if the pressure is lowered to 0.9 atm and the temperature is increased to 40 degrees Celsius. Okay. So the only changes we have to make here before we can plug these in is going to be to add our 273 to both. So we'll have 293. And 313. These are our Kelvin temperatures. And now we can plug in our variables. And this time, instead of solving for P2, we'll solve for V2. All right. Okay, and again, we'll isolate our variable of interest by multiplying both sides by the reciprocal of the values that we want to move over. So our 313 will cancel out and our 0.9 atmosphere will cancel out. And we'll multiply our left side by that reciprocal value as well. And we see that our units all cancel out. All right, and we end up with 17.8 liters as our new volume, which most closely matches answer choice D. These are all well, depending one significant figure really. So the closest answer choice here is going to be 18 liters. All right. Question number 41 asks us to, we'll just kind of look at this one on the document. The conditions expressed in the abbreviation STP, this one says do not include, right? So when you're looking at STP, that's going to be standard temperature and pressure. And it's going to be every temperature that's equal or equivalent to 0 degrees Celsius. So standard temperature. I will actually write this part down before we go through and mark them off. So this is going to be anything equivalent to 0 degrees Celsius. So 273 Kelvin. Both, I'll get rid of those things. Both of these temperatures are standard temperature. Standard pressure is going to be anything equivalent to 1 atmosphere. Okay, so that's going to be 1 atmosphere. It's going to be 760 millimeters of mercury or 760 torr, 14.7 psi, anything that is equivalent to 1 atmosphere. Okay, so when we look back at that list that they've given us, we just need to go through that list and we need to see which of those values are standard values and which ones aren't. We know that 0 degrees Celsius is okay. 14.7 psi, that's okay. 760 millimeters of mercury is fine. 1 atmosphere is fine. The only one that's not fine here is 1 torr, because the standard pressure value for torr would be 760. Okay. For number 42, the molar volume of argon gas, atomic number 18 is. The only thing that could be a little bit misleading about this question is the specific naming of a particular gas. So like they named argon gas in particular here. It does not matter what the gas is. The molar volume of every gas is the same. The molar volume tells us that 1 mole of any gas at standard temperature and pressure is going to be 22.4 liters. It doesn't matter what the gas is. 1 mole of any gas at standard temperature and pressure is 22.4 liters. That's how much space it occupies. Okay. If you have more than 1 mole of gas, then the volume will be larger than 22.4 liters. And if you have less than 1 mole of gas, then the volume will be less than 22.4 liters. But the definition of molar volume is that at STP, standard temperature and pressure, 1 mole of gas equals 22.4 liters of space. Okay. The next question, I believe, is linked to standard temperature and pressure. Both of these next two questions are. So the first question says, what volume does 76 grams of fluorine gas occupy at STP? So our job is going to be to see how many moles of gas 76 grams equals, and then we can relate it to our molar volume. And then the next question is how many moles of neon is going to occupy 2 liters at STP? We know that every 1 mole of gas occupies 22.4 liters. So we should be able to use that relationship to figure out how many moles are taking up 2 liters of space at STP. All right. So first things first, question number 43. I guess for starters, for question number 43, you have to be aware of what the formula of fluorine gas is. We're at the point in the semester where they are not going to always tell you the chemical formulas of the substances that they're mentioning because some of them you're expected to know at this point. Fluorine gas has a chemical formula of F2. It's a diatomic element. And for this question, they're asking us to take our grams of fluorine gas and then convert it into moles of fluorine gas using our molar mass. And then once we have moles of our fluorine gas, we'll convert it into liters of gas. And we'll do this using the molar volume because we're at STP. We can use the molar volume because we are at STP. Okay, if we weren't at STP, they would have to give us the temperature and they would have to give us the pressure for us to find the volume. So our molar volume tells us that 1 mole of any gas equals 22.4 liters. It's always good to write out these equalities. And our molar mass for our fluorine is going to be 2 times 19 0. So it's going to be 38 grams per mole. We can rewrite our molar mass, and I'm going to actually write it out with the correct number of significant figures there. When we write our molar mass out as an equality, it'll look like this: 38 grams of F2 equals 1 mole of F2. And then we can use these two equalities that we've written out to help us work through these steps that we've laid out here. So we'll take our grams of F2 that they've given us in the problem. They're telling us that we have 76 grams of F2. And then our first step is going to be to use our molar mass to convert the grams of F2 into moles of F2. When we do this setup with the molar mass, we know the grams go on the bottom because the gram unit is what we're given to start with. So 76 divided by 38 is just going to be 2. And the unit is going to be moles, not grams. And now in our second step, we'll use our molar volume to turn that into liters. So we know that every 1 mole of any gas is going to be 22.4 liters. So our mole unit cancels out. So if we have 2 moles of gas, we're going to end up with 44.8 liters of gas, which is answer choice C on our worksheet. All right. Okay, now question number 44. how many moles of neon occupy 2 liters at STP. Okay. Again, this right here tells us that we're able to use molar volume. Which is, again, we'll just keep rewriting it to remember. 1 mole of gas is 22.4 liters. Okay, so I know that I have 2 liters of neon. And I know that there's going to be 22.4 liters in every 1 mole. So I'm going to cross out my liters unit. Uh, 0.0893 moles, which we can round to 0.09 moles to match our answer choices. And that's going to be option B. All right. So that's how we're going to use our molar volume to figure out quantities. Okay, let's take a look at our next couple of questions are going to be utilizing the ideal gas law. So let's take a look at those. When you're trying to figure out, like, again, I know that there's a lot of equations that are part of this chapter, but they're actually all part of the ideal gas law equation. Even the simple gas laws that we've already looked at, they all stem right from this ideal gas law relationship. It's how pressure, volume, temperature, and amount of gas are related to each other. You'll know that you have to use the ideal gas law versus a different type of gas law when each gas property is only mentioned one time. So like in this case, they're telling us that we have 25 grams, which is an amount. They're telling us the volume is 50 liters. The pressure is 630 millimeters of mercury. And they're asking us to find the temperature. So they've given us 3 values. They want us to find the 4th value. Okay. So it's not like they're in the last questions we looked at, they changed values. They gave us a pressure and a volume, then they gave us a different pressure and said, find a new volume. That's not what happened here. In this case, they said, here are our 3 of our values, find the 4th value. So when we are given 3 of those pieces of information, we need to find the 4th. That's going to indicate that we have to use the ideal gas law. Okay. Similarly, in number 46, when it says what volume, in this case, we're trying to find the volume, will 2.5 moles of hydrogen gas occupy when our pressure is 1.3 atmospheres and our temperature is 35 degrees Celsius. So here they gave us the amount, the pressure, and the temperature, and they're going to want us to find volume. All right. So 45 and 46 are both examples where we're going to have to use the ideal gas law to find the missing piece of information. And the ideal gas law is going to be PV equals nRT. Your P value is going to be pressure in the unit of atmosphere. V is going to be your volume, specifically in the unit of liters. N is going to be the amount of gas, specifically in moles. And your T is going to be your temperature, specifically in Kelvin. All of these units have to be specific because you have this R value as part of your ideal gas law. This is your gas constant. The numerical value of your gas constant depends on the units that you use to find it, okay? We're going to use the gas constant 0.0821 and watch the units of this gas constant: liters times atmosphere over moles times Kelvin. So they're all the same units that we've just listed out here. So we use this number and we make sure that our pressure is always in atmosphere, our volume is always in liters, our amount of gas is always in moles, and our temperature is always in Kelvin. Okay. Now let's look at question number 45 and we'll look at the information that they've given us. They're telling us that we have 25 grams of N2 at a volume of 50 liters and a pressure of 630 millimeters of mercury. Okay, and they're asking us to find the temperature. So this is going to be our amount. This is going to be our volume. This is going to be our pressure. And one at a time, you're going to go through and you're going to say, all right, well, my amount has to be in moles. So I'm going to have to take my grams and I'm going to have to turn it into moles. My volume has to be in liters. It's already in liters, so that's okay. My pressure has to be in atmosphere. So I'm going to have to take my millimeters of mercury and I'm going to have to turn it into atmosphere. All right, but make that list for yourself so that you don't forget to change the values that have to get changed. All right, so for our first one, we have our 25 grams of nitrogen. If we want to change that into moles of nitrogen, we're going to have to use the molar mass. The molar mass of nitrogen is going to be 2 times the nitrogen mass, which is 14.01. So that's going to be 28.02 grams of nitrogen in every 1 mole of nitrogen. All right, so there's our amount value that we can actually use in the ideal gas law. For our pressure, 630 millimeters of mercury. I need to convert that into atmosphere. There's 760 millimeters of mercury in every 1 atmosphere. And now I have a pressure value that I can use in my ideal gas law. So now I've got PV equals nRT, and I want to find my temperature value. So I'm going to divide both sides by nR. So what I'm going to be left with is pressure times volume over N times R equals my temperature. So now I can plug that in. My pressure is going to be 0.829 atmosphere. My volume is going to be 50 liters. My N value is going to be 0.892. And my R value, 0.0821. Notice how your units are all going to cancel out except for your temperature unit, which makes sense because we're solving for temperature. Okay, and at the end of all that, we get 566 Kelvin as our temperature value. Okay, and that's going to be closest to answer choice C. All right. Let's look at question number 46, which is another version of our ideal gas law. All right, so here they're telling us that we have 2.5 moles of H2. They want us to find the volume. So it says, what volume will 2.5 moles of H2 gas occupy at a pressure of 1.3 atm and a temperature of 35 degrees Celsius? Okay, so again, this is our amount. This is our pressure. This is our temperature. Our amount has to be in moles. Good. Our pressure has to be in atmosphere. It's good. Our temperature has to be in Kelvin. So we're going to add 273 to this. Okay. And now we're good to solve for our ideal gas law. So we've got PV equals nRT. And if we're going to solve it for volume, then we're going to divide both sides by pressure. Volume equals nRT divided by P. So we're going to have 2.5 moles times our R constant times our temperature in Kelvin. And we're going to divide all of that by our pressure of 1.3 atm. And we get a volume of 48.6 liters, which we can round to our 2 sig figs. And that's going to be answer choice D. Okay. All right. Let's look at the next two questions. We're going to move a little bit into the partial pressure section now. First question here asks, which gas has the highest partial pressure in the atmosphere? This question in general requires you to have paid attention to when we were reading about the makeup of the gases that are in the air that we breathe, our atmospheric gases, and understanding that whichever gas is present in the largest quantity is going to have the larger partial pressure. Partial pressure is going to be based on amount. So the more of a particular gas that is present, the higher that gas's partial pressure will be in relation to the other gases that are present. So in the atmosphere, the most prevalent gas is nitrogen by a long shot. So nitrogen's partial pressure is going to be the highest. Question number 48 is asking us to work a little bit with partial pressures and total pressures and asking us to apply Dalton's law of partial pressure. This one says that we have a mixture of 3 gases, A, B, and C, and the total pressure is 8.5 atmosphere. They're telling us the pressure of gas A and the pressure of gas B, and they're asking us to find the pressure of gas C. Okay, so let's take a look at how we work at that one. Remember that Dalton's law of partial pressures tells us that our total pressure is going to be the sum of all of the partial pressures in our mixture. So in this case, we have three gases that make up our mixture. We have gas A, B, and C. So what Dalton's law tells us is that our total pressure is going to be gas A pressure plus gas B's pressure plus gas C's pressure. They told us that total pressure value, said it was 8.5 atm. They told us the pressure of gas A. They told us the pressure of gas B. And they want us to find the pressure of gas C. All right. So we can just take our 8.5 and we can subtract 2.4 atm and subtract 1.7 atm. And then what we're left with is going to be the pressure for gas C. Okay, so 8.5 minus 2.4 minus 1.7. Pressure of gas C is going to be 4.4 atmosphere. Right, which is answer choice B. The next question on here is again another one of like more of our reading type questions. We talked a little bit about the relationship between oxygen and carbon dioxide in the blood versus the tissues. So if you have a certain lung ailment like emphysema, where there's a decrease in the ability of oxygen to diffuse blood, they're asking, would that mean the partial pressure of oxygen in the blood be higher than normal, lower than normal, the same, or be toxic? If your blood has a decrease in the ability, if there's a decrease rather in the ability of oxygen to diffuse into the blood, that means oxygen's having a hard time entering the blood. So there'll be less oxygen in the blood. And if there's less gas present, then the partial pressure of that gas is lower. Because again, partial pressure is going to be based on amount. So if you have less of that gas present, the pressure of that gas is also going to decrease. Okay. All right, let's take a look at the next two questions. Do some calculations with these ones. So here we have a 0.49 mole sample of oxygen in a 4.8 liter container at 25 degrees Celsius. What is the pressure in the container? So that looks like an example of our ideal gas law. And then question number 51 is asking us, what is the partial pressure of oxygen in a mixture that contains 0.3 moles of oxygen, 0.70 moles of nitrogen, 0.250 moles of argon at a total pressure of 1.1 atmosphere. So we'll look at how to do that question as well. All right, but first of all, question number 50. We're told that we have 0.49 moles of oxygen gas. So that's our amount. We have 4.8 liters. That's going to be our volume. We have 25 degrees Celsius. It's going to be our temperature. And we're going to find our pressure. Okay. So for our temperature, we're going to add our 273 to this. So now our temperature unit's okay. And now we can use our ideal gas law. We can divide both sides by volume so that we can isolate our pressure value. Pressure is going to be nRT divided by volume. So we're going to have 0.49 moles of oxygen times 0.0821, which is our gas constant, times our temperature of 298 Kelvin. All of that divided by our volume of 4.8 liters. And we get a pressure of 2.5 atm. Okay. The next one still have to be a little bit more conceptual. It's based on what we've talked about with Dalton's law of partial pressure. They're telling us that we have 0.3 moles of oxygen, 0.7 moles of nitrogen, 0.25 moles of argon, and we have a total pressure of 1.1 atmosphere. Okay. So we said that partial pressure is based on the amount of gas that's present. So what we know is that if this is our gas mixture, all right, the gas that is present in a larger amount, like nitrogen, is going to have a pressure that's higher than the gases that have lower amounts, right? So nitrogen has 0.7 moles in this mixture. So the pressure of nitrogen is going to be higher than oxygen or argon, which both have lower pressures. We also know that the pressure of oxygen plus the pressure of nitrogen plus the pressure of argon is all going to add up to 1.1 atmosphere, which is our total pressure. What we can do, though, is we can look at the amount of gas that's present, and we can take like a percent or a fraction, and we can use that to figure out how much of this total pressure just belongs to oxygen. Okay. So if we look at all these gases that are present, we have 0.3 moles of oxygen, 0.7 moles of nitrogen, 0.25 moles of argon. If I add all these moles together, right, I'm going to have 1.25 moles of gas total. Okay. So I can say that my percent or my fraction of oxygen gas is going to be 0.30 moles out of the 1.25 moles, right? This is how much of my total gas is just oxygen gas. So if I was turning this into a percent, I would take my 0.24 and I could multiply it by 100. And I could say that 24% of the gas mixture is oxygen gas. Okay. That's what this means. It means that this is all of my gas, all three of them mixed together. 0.30 moles of that is just oxygen. So 24% of all of the gas in that mixture is oxygen gas. But what that means for the pressures, it means that 24% of the 1.1 atmosphere is oxygen's pressure. Okay. It means that 24% of this belongs to oxygen. So if I want to figure out how much of this pressure belongs to oxygen, I'm going to take my total pressure, I'm going to multiply it by the fraction of it that belongs to oxygen. So my pressure for my oxygen is going to be the oxygen's decimal, oxygen's fractional value, which is actually called a mole fraction, but we didn't give it a name. I'm just going to call it X for now. So that's the fraction of gas that belongs to oxygen. And we're going to multiply it by the total pressure. So the pressure of oxygen is going to be our 0.24 times 1.1 atmosphere. So oxygen's fraction times the total pressure. So this value right here is going to be the pressure of just the oxygen. Okay. We could do that for all of the gases in that mixture, but we just do the same set of steps. If we wanted to do it for nitrogen, we could say, all right, well, I can look at the moles of nitrogen. For nitrogen, I know that there's 0.70 moles. And I know that my total moles are 1.25. So the fraction of my gas that's just nitrogen is going to be 0.56. This is nitrogen's fraction. And to find the pressure for nitrogen, I'm going to take nitrogen's fraction and I'm going to multiply it by that total pressure. So nitrogen's pressure is going to be 0.616 atm. Okay. We could do the same thing for the argon. So we've done it for oxygen, we've done it for nitrogen, let's do it for argon. For argon, we have 0.25 moles. And we'll divide that by our total number of moles. Okay, and this is argon's fraction. And to find the pressure for argon, we're going to take argon's fraction and multiply it by our total pressure. But look what happens. Nitrogen's moles were the biggest. Nitrogen's pressure is the biggest. Oxygen was middle. Oxygen's pressure is in the middle. Argon's amount was the lowest. Its pressure is the lowest. Argon and oxygen also have amounts that are kind of close. Their pressures are kind of close. The other thing that you're going to see, because we just found the pressure of all these individual gases, watch what happens when we add all three of them together. So if we do the pressure of oxygen plus the pressure of nitrogen plus the pressure of argon, so that's going to be 0.264 atmosphere plus 0.616 atmosphere plus 0.22 atmosphere 4 plus 616. I get 1.1 atmosphere back out. So this is like doing pressure of A plus pressure of B plus pressure of C equals total pressure. Okay. All right. Let's take a look at the next question. Number 52. This one's asking us to look at a series of statements and choose the one that's incorrect, if any. So first statement says, breathing illustrates Boyle's law. Nothing wrong with that statement. That's true. Breathing is showing us that as our lung capacity increases, the volume of our lungs increases, the pressure that they're experiencing decreases. So that's a correct statement. Charles' law illustrates that the volume of a gas expands or increases when the temperature becomes higher. Yep, that's exactly true. That's showing a directly proportional relationship. Avogadro's law illustrates that the volume of a gas is proportional to its mole number. So the volume is going to get larger as the mole number gets larger, or the volume is going to get smaller as the mole value gets smaller. That's also true. Yeah, so all of those choices, A, B, and C, those all make sense. All right, next question. A gas sample has a volume of 178 milliliters at 0 degrees Celsius. The temperature is raised at constant pressure until the volume is 211 milliliters. What is the temperature of the gas in Celsius at this volume? So they're taking our, they're giving us rather the volume and the temperature. They're telling us that the pressure is constant, and then they're changing the volume, and they're asking us for the new temperature. So they're focusing specifically on volume and temperature in this question, which is an example of Charles' law. Okay. If it's Charles' law, then we know it's going to be V1 over T1 equals V2 over T2. They're telling us that our initial volume is 178 milliliters. Our initial temperature is 0 degrees Celsius. Our new volume is 211 milliliters. And they want us to find the new temperature in Celsius. Okay. That's fine, but remember that we can't use Celsius in this equation. So we still have to add our 273. I'm going to put the 0.15 in this case because they gave us decimal places to work with. So we have to make sure to change this into Kelvin before we plug that in. They also want us to find a temperature. So remember that when we're finding that second temperature value, our temperature is going to end up on the opposite side in the numerator position. And the reciprocal of what's left on your left side will end up over here on your right side. So when we rearrange this equation, we're going to end up with T2 equals V2 times T1 over V1. All right. And we can plug in our values from there. V2 is going to be 211 milliliters. T1 is going to be 273.15 Kelvin. Divided by V1 is going to be 178 milliliters. Our milliliters will cancel out. And we're going to end up with 324 Kelvin. Notice the answer choices here. Um, this is the number that we get in our calculator. If you are not writing out your units, then it's going to be really easy for you to see this number and to pick this answer choice. But our units here don't match. This is not the right answer. Okay. Uh, the only thing that we know for sure right now is that our initial temperature was 0, right? Our original volume was 178. Our volume went up to 211. So our new temperature has to be greater than 0. So we know that choice A can't be the right answer. And we know that choice C can't be the right answer. We've just eliminated choice B as well. So we're down to these two. So we're going to take our 324 Kelvin. We're going to subtract 273 from it. And we end up with 51 degrees Celsius. And this is going to be our correct answer. You got to make sure that you're writing down those units along with your solutions, or else you're not always going to see the trap that they're laying down there, right? They're trying to make sure that you really understand the relationship between the number and the corresponding unit. Question number 54 asks, which of the following has the greatest volume at STP? Okay. STP meaning standard temperature and pressure. Um, and remember, when we are at standard temperature and pressure, we're able to use our molar volume, and our molar volume says that one mole of any gas equals 22.4 liters. Okay. And so they're giving us 4 gas samples here. They're giving us 5 grams of hydrogen, 5 grams of nitrogen, 5 grams of oxygen, 5 grams of carbon monoxide. Okay. In order for me to figure out their volume, I'm going to need to turn these gases from grams into moles, right? Once I turn my grams into moles using the molar mass, then I can go from moles into liters using my molar volume. So for each of these samples, I can use my periodic table and I can look at the molar masses of each gas. Right, this would be my first step for each of these, is to use the molar mass. Okay. So I'm going to do that calculation for each one of these. So 5 grams of hydrogen means I'm going to have 2.48 moles of hydrogen. 5 grams of nitrogen means I'm going to have 0.178 moles of nitrogen. 5 grams of oxygen means I'm going to have 0.156 moles of oxygen. And 5 grams of carbon monoxide means I'm going to have 0.179 moles of carbon monoxide. Once I have these mole values, now I can use my molar volume. And my molar volume tells me that 1 mole of any gas is 22.4 liters. So I can take my mole values and I can multiply it by 22.4 to see how much volume it's going to take up. So 2.48 times 22.4 is going to give me 56 liters. We probably can see without even doing the rest of this math that whichever gas sample had the biggest number of moles is going to have the largest volume, right? So hydrogen, whose molar mass is the smallest, 5 grams of hydrogen is going to be a lot more moles of hydrogen than any of these other samples. But if you don't feel comfortable making that association without proving it to yourself, then you can just go through and use the molar volume for each one, and it'll show you. Okay, so clearly our winner here is going to be our hydrogen with 56 liters. All right, let's put up some of these next questions. All right, so for number 55, they're asking us to find the pressure of 1.78 grams of nitrogen that's confined to a volume of 0.118 liters at 25 degrees Celsius. So in that case, they're asking us to find pressure. They're giving us the other values. So that'll be the ideal gas law. Number 56 asks the number of moles of an ideal gas in a 2.5 liter container at 27 degrees Celsius and a pressure of 6.62 psi is. So here they're asking us to use the ideal gas law and solve for the moles of gas. Number 57 is asking us to do a little bit of stoichiometry. They're asking us to use that balanced equation to help us answer the question. How many grams of calcium hydride, CaH2, are required to produce 4.56 liters of hydrogen gas at 25 degrees Celsius and 0.975 atmosphere? So we'll work through that one and we'll kind of go through, we'll try to remind ourselves of the steps that we have to do there. Start with those. So for number 55, we've identified it as an ideal gas law equation, PV equals nRT. They're telling us that we have 1.78 grams of nitrogen. Our volume is 0.118 liters, and our temperature is 25 degrees Celsius. And they want us to find the pressure. Okay, so the two things that we see here that we need to fix, we have to turn our grams into moles. we have to turn our Celsius into Kelvin. So that one's easy. For our grams of nitrogen, we'll make that switch using the molar mass. There's 28.02 grams of nitrogen in 1 mole. Okay. And now I can find my pressure. Pressure, remember, we'll divide both sides by volume to isolate the pressure. So pressure is going to be nRT divided by volume. So there's our mole value. Here is our gas constant. Here is our temperature. And our volume is going to be 0.118 liters. Right, and we end up with a pressure of 13.2 atmosphere. Okay. Number 56 is another ideal gas law equation. This time they're asking us to find the moles. They're telling us that we have a 2.50 liter container. The temperature is 27 degrees Celsius and the pressure is 6.62 psi. So they've given us temperature and pressure that we're going to have to change into the correct units before we can solve this equation. In this case, we'll be solving it for moles. Okay. So we'll add our 273. And for our pressure, we know that there's 14.7 psi in 1 atm. Okay, so now we can solve our ideal gas law for moles. So we'll divide both sides by RT, and we'll end up with PV divided by RT equals N. So that'll be 0.450 atm times 2.50 liters divided by 0.0821 Kelvin divided by 300 Kelvin. Cancel out all of our units. The only unit that we have left is going to be our mole unit. And we end up with 0.0457 moles of gas, which is answer choice A. Okay. All right, so for number 57, we have a balanced equation that we're going to be looking at. Okay, and they're telling us here, they're saying how many grams. And again, if you look at a question like this and you're not sure how to approach it, start by writing out your equation and then listing the information underneath the parts of the reaction where information is given. So here they're saying like how many grams of the calcium hydride. So we'll put a question mark in grams here. So we know at least what we're focused on finding. Are required to produce 4.56 liters of hydrogen gas at 25 degrees Celsius and 0.975 atmosphere pressure, according to the following equation. Okay. With this information, because here we're looking at a gas and we have the volume, the temperature, and the pressure, we can use all of this information to find the moles using PV equals nRT, using our ideal gas law. We can find our moles of gas. Once we find the moles of gas, then we can find the moles of our calcium hydride using our balanced equation. Once we know the moles of our calcium hydride, we can find the grams of it using the molar mass. Okay, so our order here, our order of operations is going to be to find the moles of H2, and then we're going to find the moles of CaH2, and then we're going to find the grams of CaH2. Okay, so for this part, we're going to use PV equals nRT. For this part, we're going to use our balanced equation. And then for this part, we're going to use our molar mass of CaH2. So before we start, we're just going to add our 273 to our temperature so that it's in Kelvin. And we can solve our ideal gas law equation. This will be our step one. We'll take our PV equals nRT, and we're going to solve it for our moles. So moles is going to equal PV divided by RT. So 0.975 atmosphere times 4.56 liters divided by our R value. Divided by our temperature. And that's going to be our moles of hydrogen. Okay. Now, step two, we're going to find the moles of our calcium hydride. If we have 0.182 moles of hydrogen, then we can look at our balanced equation and we can see that for every 2 moles of hydrogen, we're going to have 1 mole of calcium hydride. So we have 0.091 moles of CaH2. And now for our last step, we have to use our molar mass to turn moles of calcium hydride into grams of calcium hydride. So we're going to calculate the molar mass of CaH2. So calcium is 40.08 plus 2 times 1.008. Okay. So third step, if we have 0.0910 moles of CaH2, we know from our molar mass that every 1 mole is going to be 42.096 grams. Which means we'll end up needing 3.83 grams of CaH2 to make our 4.56 liters of hydrogen gas. Okay, which is closest to answer choice A. All right, let's look at question number 58. They're giving us another balanced equation to work with here. So we'll start off by writing our balanced equation and then sort of, again, just listing the information that they give us underneath the balanced equation so that we can figure out what we need to do. All right, so it says how many liters of hydrogen gas are needed? So put a question mark here. How many liters are needed to produce 110 grams of water at 25 degrees Celsius? I mean, you could put the 25 degrees Celsius and the 1 atmosphere off to the side if you want, but the temperature and the pressure, they kind of go with whatever the gas substance is, because we're going to end up using, if you think about the ideal gas law, we're going to end up using the volume, or we're going to end up using the moles and the pressure and the temperature to find the volume. So even though the temperature and the pressure is true for your whole reaction, it's going to be more useful to the gas component that we're going to be focusing on with our ideal gas law. So the only real difference in this example versus the last one is the direction that we're going to go with our calculations. Because we're going to start here with the grams of H2O. And we're going to turn that into moles of H2O. And once we have moles of H2O, we're going to turn that into moles of hydrogen gas. And then we're going to use our ideal gas law to turn that into liters of hydrogen gas. Okay. So our grams to moles, we're going to do that with the molar mass of our H2O. We're going to go from our moles of water to our moles of hydrogen with our balanced equation. And then we're going to go from the moles of hydrogen to the liters of hydrogen with our ideal gas law, solving it for volume. Okay. So step 1, we're going to take our 110 grams of H2O. We can find the molar mass for H2O by adding up 2 hydrogens plus 1 oxygen. So that's going to be 18.02 grams. per mole. Okay, and once we have our moles of H2O, now we can do that second step with our balanced equation. Every 2 moles of H2O is going to require 2 moles of hydrogen gas. So if we make 6.10 moles of H2O, that means that we're going to need to be reacting 6.10 moles of hydrogen gas. Okay, now that we have the moles of hydrogen gas, we can use our PV equals nRT equation to solve it for volume. We just want to make sure that we have our temperature in terms of Kelvin. Once again, I'm using the decimals for Kelvin here because they gave us a temperature that had some decimals in it. So here we're going to, in our third step, we can consider this part step 2, and then this part will be step 3. We'll take our PV equals nRT equation and we'll solve it for volume. So that will be nRT divided by pressure. So we're going to have 6.10 moles times our R constant times our temperature divided by our pressure. Right, and we're going to end up with 149 liters of hydrogen, which is going to be answer choice D. All right. Our next question, number 59. Says, what mass of NO2 is contained in a 13-liter tank at 67.33 psi and 112 degrees Celsius. Okay. So in this case, we're given a volume, we're given a pressure, and we're given a temperature, and they're asking us to find an amount, but that amount is in terms of moles, of grams rather. So we can't find the gram amount directly from the ideal gas law. From our ideal gas law, we can find moles. Once we have moles, then we can turn it into grams. Okay. So we're going to use our ideal gas law to find moles of NO2. And then we're going to find grams of NO2 using our molar mass of NO2. Okay. But before we do that, we have to take our pressure and our temperature, and we have to convert that into our ideal gas law units. And we're going to have our 112 Celsius. We'll add 273 to that. And so now we can take our PV equals nRT and we can solve it for our moles of NO2. That will be equal to PV divided by RT. So 4.58 atmosphere, 13 liters. Our R constant and our temperature. Um, and then we're going to take our moles of NO2 and we're going to find the grams of it using the molar mass. The molar mass for NO2 is going to be 1 nitrogen plus 2 oxygens which is going to be 46.01 grams per mole. So we're going to take this will be step 1. This can be step 2. We'll take our 1.88 moles of NO2. Every 1 mole of NO2 is going to be 46.01 grams. We're going to end up with 86.5 grams of NO2. And that's going to be closest to answer choice B. All right. Our next question. Let me share the screen again so just so we could look at the wording of it. A tank contains argon gas at 9.48 psi, helium gas at 571 torr, neon gas at 519 millimeters of mercury, and they want us to find the total pressure in atmosphere. Okay, so we're going to have to essentially take each of these values, convert them into atmosphere, and then add them together for us to figure out what the total pressure is going to be. This question requires us to know how to find the total pressure from partial pressures, which is Dalton's law of partial pressures, saying we have to add everything together. But it's also asking us to recognize the fact that when we add our pressure units together, those pressure units all have to match each other. And in this case, we'll convert everything into atmosphere because they want the answer to be an atmosphere. So there's no reason to keep the units in anything else. So we'll have 9.48 psi. For our argon, we'll have 571 torr for our helium, and we'll have 519 millimeters of mercury for our neon. And now for each of these, we'll convert them into ATM. So there's 14.7 psi in every 1 ATM. There's 760 torr in every 1 ATM. And there's 760 millimeters of mercury in every 1 ATM. $571 divided by 760 is going to be 0.751 ATM. And then 519 divided by 760 is 0.683 ATM. Now we'll add all of those together for our total pressure. We end up with a total pressure of like 2.08 atmosphere. Okay. All right, I'm going to share the screen for our last 5 questions here. These ones sort of go back to some of the stuff that we did in chapter 7, but I just want you to have a look at them before we go through them. There's a lot of just different conversions that we're going to go through here. 61's asking us to calculate the molar mass. Then 62 through 65 are asking us to find different parts, different things in different conversions. So we'll just focus on each one. Okay, so for starters, number 61, we're calculating the molar mass of calcium phosphate. So when you're calculating your molar masses, you're going to remember that your subscripts are going to apply to the individual element that they're attached to. So the 3 applies to the calcium, and the 4 in here applies to your oxygen. Subscripts that are attached to the parentheses apply to everything inside the parentheses. So the 2 applies to the oxygen and to the phosphorus. Okay. So within your compound, you've got calcium, you've got phosphorus, and you've got oxygen. For our calcium, we've got 3 of them. For our phosphorus, we have 1 times 2. So we have 2 total. And for our oxygen, we have 4 times 2. So we have 8 total. And so we're going to look up each value. Sorry, those should not have been colons. We're going to look up each molar mass value on the periodic table. And we're going to multiply the number of atoms we have by that particular element's molar mass. So calcium is going to be 3 times 40.08. Phosphorus is going to be 2 times 30.97. Oxygen is going to be 8 times 16. And then we'll add all those together. So we end up with answer choice E. That's going to be our molar mass for our calcium phosphate. All right. Question number 62 says how many moles of CaCl2 are in 3.27 times 10 to the 22 formula units. Remember that term, formula units, that's the term that we use to describe 1 unit of an ionic compound. So instead of the word molecule, when it's an ionic compound, we use the phrase formula units. But it works the same way as the word molecule works for molecular compounds. Um, when we're going between moles and formula units, just like with moles and molecules, we're going to connect those using Avogadro's number. And Avogadro's number says that 1 mole of anything is going to be 6.02 times 10 to the 23 of that thing. So if I have 1 mole of CaCl2, that's going to be 6.02 times 10 to the 23 formula units of CaCl2. So if I'm starting out with 3.27 times 10 to the 22 formula units, then when I set up my conversion factor, my Avogadro's number with my formula units has to go on the bottom. So that my units cancel out. And my 1 mole goes up top. And again, I know I said this in class, but I'm going to say it again. When you're using your scientific calculators, if you're not really sure how to input the scientific notation on them properly, if you have a calculator that has parentheses, put this exponential term in parentheses so your order of operations doesn't get accidentally messed up. If you know how to use the scientific notation keys, then that's fine. Your order of operations won't get messed up by this. But if you're getting an exponent that's in the 40s, that's because you didn't put the number into your calculator correctly. And now you're seeing an exponent that's way larger than it should be. Okay. What you should be getting back out of this is going to be 0.0543 moles, which is answer choice B. So yeah, if you're not getting that number back out, if you're getting a really large exponent, then come find me and we have to talk about how you're putting the numbers into your calculator. And it's something that we can fix very easily, but you have to get it fixed before you take the test. You can't be sitting there during the exam and then ask, like, why aren't my numbers making sense? Because it's too late at that point. Can't help. All right, number 63. How many molecules of C6H12O6 are in 0.596 grams? That should have said of glucose. So we'll fix it here. Okay, how many molecules are in 0.596 grams? We know from what we talked about that if we're starting out with grams, the only thing that we can do when we have a value in grams is to use the molar mass and convert it into moles. There is no direct conversion from grams into molecules. But once we have our compound in terms of moles, then we can use Avogadro's number and we can convert it into molecules. Okay, so grams to moles, we're going to use molar mass. Moles to molecules, we're going to use Avogadro's number. Okay, so to use our molar mass, we need to find that first. For carbon, it's going to be 6 times 12.01. For hydrogen, it's going to be 12 times 1.008. For oxygen, it's going to be 6 times 16. We're going to add all that together. Okay. So step one, we're starting out with our 0.596 grams of our glucose. There's 180.16 grams in 1 mole. And according to Avogadro's number, there's going to be 1 mole for every 6.02 times 10 to the 23 molecules. 1 mole for every 6.02 times 10 to the 23 molecules. Which is going to give us 1.99 times 10 to the 21 molecules of glucose. Okay, which is going to be answer choice D. Okay. Question number 64. Is how many hydrogen atoms are in 0.750 grams of NH4Cl. Okay, so for this one, we have a little more that we need to do. We have grams of NH4Cl, which we will be able to turn into moles of NH4Cl using our molar mass. From our moles of NH4Cl, we're going to be able to turn that into formula units because this is an ionic compound. Remember, formula units work like molecules. And then once we know how many formula units we have, then we can focus specifically on the number of hydrogen atoms that are present using our chemical formula. Okay, so this is going to be molar mass. This step is going to be Avogadro's number. And this step will be our chemical formula. All right. For NH4Cl, our molar mass is going to be 14.01 plus 4 times 1.008 plus 35.45. Okay, so there's our molar mass for our ammonium chloride. Now, when we're writing out, like once you have your steps down, you can also write the equalities out like underneath the steps to help you set up your calculation. For our molar mass, what we know from the molar mass is that every 1 mole of NH4Cl is going to be 53.492 grams. From Avogadro's number, we know that every 1 mole is going to be 6.02 times 10 to the 23 formula units. And we know from the chemical formula that every 1 formula unit of NH4Cl contains 4 hydrogen atoms. And that sort of sets up the calculations that we'll need to do. We're starting off with our 0.750 grams of NH4Cl. Our first step is going to be to take our grams and turn them into moles. So our 53.492 grams goes on the bottom, and our 1 mole goes up top. Okay, that's step 1. Step 2 is that we can take our moles of NH4Cl, and every 1 mole equals 6.02 times 10 to the 23 formula units. Okay. And then for step 3, we'll take our number of formula units, put it over here. So for step 3, we're going to have 8.44 times 10 to the 21 formula units. And we know from our chemical formula that every 1 formula unit of NH4Cl, we're going to have 4 hydrogen atoms. So we can take our number of formula units and multiply it by 4. Okay, so we're going to end up with 3.38 times 10 to the 22 hydrogen atoms, which is going to be choice A. And question number 65, which is our last question on this review sheet, is real similar. It's asking us for the number of oxygen atoms in 27.7 grams of aluminum nitrate. Okay, so if you tried the last one and now you just watch me do the solution for it, definitely pause and try this one on your own and see if you can trace through these steps. Okay, because this is real similar to what we just did. They're giving us 27.7 grams of aluminum nitrate, and they're asking us to find the number of oxygen atoms. Okay, so we're going to have to go from grams of aluminum nitrate to moles of aluminum nitrate into formula units of aluminum nitrate, because this is an ionic compound. And then from formula units into oxygen atoms. Okay. we know we're going to need the molar mass. So let's calculate that out first. From our chemical formula, we know we have 1 aluminum. We have 3 nitrogens. And we have 3 times 3 is going to be 9 oxygens. Okay, so we'll add all that together. All right, so our first conversion, which is going to be our molar mass, the equality for that is going to be every 1 mole equals 213.01 grams of aluminum nitrate. Our second conversion, which is going to be moles to formula units, is going to be Avogadro's number. Which will be 1 mole equals 6.02 times 10 to the 23, in this case, formula units. And then our last conversion will be from formula units into oxygen atoms. And for this, we'll look at our chemical formula. And every 1 formula unit of ALNO3 has 9 oxygen atoms. All right, so we start off with 27.7 grams ALNO3, and we're going to use our molar mass. That tells us for every 213.01 grams, that's going to be 1 mole of ALNO3. So now we have 0.130 moles of ALNO3. And now we can use Avogadro's number. That tells us every 1 mole is going to be 6.02 times 10 to the 23 formula units. And we'll write down the answer over here. So that's going to be 7.83 times 10 to the 22 formula units. And again, you got to be real careful because you'll notice on the answer choices for this question, well, let's finish the question and then we'll look at the answer choices they gave us. So we took our moles of aluminum nitrate, we multiplied it by Avogadro's number, and now we know how many formula units there are of aluminum nitrate, which remember, that works the same way that molecules work. And now we look at the chemical formula, and for every 1 formula unit of aluminum nitrate, we're going to have 9 oxygen atoms. So we're going to end up with 7.05 times 10 to the 23 oxygen atoms. Which is answer choice D. Now, if you look at the other answer choices for this particular question, I didn't look at it for the last question, but we can look at it here. Answer choice A is 0.130. Answer choice B is 1.17. Answer choice C is 7.83 times 10 to the 22. Answer choice D is the correct answer, 7.05 times 10 to the 23. And then answer choice E is 6.02 times 10 to the 23. Okay. Now, when you're looking around at all the work you did, you see some similar numbers here. Avogadro's number right here. So they're giving you a number that looks familiar. If you're doing your calculations right, 0.130 rather, you get that number in your calculator. It's not the right answer, but it's part of your calculations. And you have to know enough to understand that this is not the step that you stop at. The same thing is true over here. They put this number here as well, but that's not the step that you're stopping at, because this number tells you how many formula units you have. It doesn't tell you how many oxygen atoms there are. You're not done in this case until you get to the oxygen atoms. So you have to be keeping track step by step so you know that these things aren't what you need. Okay? And that you're not done until you get to that last step there. All right. That's the end of the review sheet. I hope you find it helpful. If you have any questions, just send me an email and we'll try to get it taken care of before your exam. Good luck studying.